Okay, good morning everyone. Welcome to the third day of this workshop. The people who are in the room were already warned, but we want to warn also the people that are assisting online. By 9, we'll have a power supply cut from the hotel. It's supposed that the things go smoothly because they have a generator, but it will take half an hour and we have again at midday. So if something happens with the live session, you already know what is happening. We'll start this day with a talk by Mr. Alexnder Barth on ocean data analysis with Julia. And Alexnder is an associate professor at the Geohydrodynamics and Environment Research Group of the University of Liège. He obtained his PhD in 2004 at the University of Liège on data assimilation in nested ocean models. After his postdoc at the College of Marine Science of the University of South Florida, he worked on variational interpolation with DIVA and DIVANT, and he is principal investigator of several European projects aiming to apply and improve these tools for generating climatologies based on in-situ observations. Recently, he also investigated the use of machine learning techniques with ocean remote sensing data. Welcome, Alexnder. Thank you.
Thank you. So, hello everybody. I will present today talk about ocean analysis with Julia. So it's a very generic talk. We'll cover different topics in this talk. So first I will speak about manipulating netCDF files with NC datasets package and a newer package called Common Data Model, which is now dependencies of NC datasets. In another, then we will talk about variation analysis with DIVA and D, and I will end up with some maybe more fun stuff with running Julia in a web browser and a student project that we made for our master student at the University of Liège. And at the very end, I probably won't have much time, but I can also speak about denoising diffusion model for reconstruction of missing data and satellite images. But yeah, I will probably show some slides really quickly at the end. So netCDF, the benefit of netCDF is a cross-platform binary format. And that allows you also to store metadata in a really flexible manner. And there are the CF convention, which gives the semantic meaning of the metadata. And one really shared concept of netCDF is the idea of shared dimensions. So assume that you have a variable called temperature, which sets the dimension x, y, and t. Yeah? You can add other variables which reuse the same dimensions. So if you subset the temperature variable, yeah, say we want to have an element 1, 2, 3, you immediately know what is the corresponding subset that you should apply to the coordinates, to longitude, latitude, and time. So, and with this simple idea of shared dimension, it now becomes really easy to represent data on a fixed grid, data on a moving grid, transect, profile. So just by looking at the shared dimensions, it becomes immediately clear how the data is structured. And so there's no hard distinction in netCDF between data and metadata. So everything, or no hard distinction between coordinates and data. So everything are arrays, and they are linked together with the named dimensions. And it's widely used in geophysics, but it's really very generic. So it can also be used in other domains. And so in NC datasets, I wrap the C library from Unidata, and so it actually by now supports several data formats. So the original netCDF format, but also HDF5 variant of this format. Remote data sets using OpenDAP. That's really handy when you some data sets are distributed via OpenDAP, and if there are a global data set and you're just interested in a subdomain like the Mediterranean Sea, you can only fetch from the remote server what you're interested in. And this is really, the downloading is really transparent. So instead of providing NC dataset a file, you would just provide an URL, and this is the same approach. And inside the netcdef library from Unidata is also now support for ZAR files, which is another format which is becoming quite popular. And just out of interest, last year I had a look at the dependency graph. So which Julia package depend on netcdf, on the C library netcdf. And so that's the green library here. And then there are actually two wrappers of this. There's the netcdf-gl and the NC datasets package. So it's quite interesting to see which package are using your code. And so on this year, the things has become a bit even more busier, which means good. So people are actually interested in using netcdf in the Julia community. And it only includes direct dependencies. So if you know that in Julia we can also have weak dependencies, but this is not included in the graph. Okay. So the API to read netcdf files aims to be fairly simple and straightforward, and aims to reuse all the concepts that we have in Julia about arrays and about dictionaries. So essentially, a netcdf file is just presented to the user as a dictionary of different variables, of different arrays. And the file and the variables can have actually attributes which are also exposed as a dictionary. So the only thing that you need to know that in the NC datasets package, there is a constructor called NC dataset. And from there, once you open the file, you access a variable just as you would access a dictionary, and you access single element just as you would access an array. And if you don't know how the variables are named, yeah, you just in your Julia session you just type ds, the dataset objects, and then it will print out all the metadata in this show function. So, and as I said before, there is this CF convention which gives some semantic meaning to some attributes. So you can declare a particular fill value, which should be considered as missing, and you can declare scale factor and offset and things like this. So this is all handled automatically. And just in case, if you have any questions, don't wait to the end. You can just raise your hand and I can take your question right away. So actually here, concerning the fill value, I'm just wondering who of you use missing as the sentinel value, as the value to declare that something is not there in Julia. Can you raise your hand if you use missing? Okay, and who use none? Oh yeah, okay, yeah, this was quite interesting. So yeah, so none is actually I'm working to make it also possible to use none as a missing value. Okay, but interesting to see that it's more popular than missing. Yeah, so as I said, if you want to subset a variable, you just index the array, yeah, just as you would do a normal Julia array. And but sometimes you want to load the data giving a certain bounding box. Yeah. So you don't know exactly what is the index 10. You just know that you are interested in saying this bounding box, this region of the world, and I want only download the data in there. So that's also now supported in NC datasets. Actually, it's implemented in Common Data Model that you can select a dataset or a variable using the values of the coordinate values. So here it means that in this example you load all the data between 10 and 20 in the longitude dimension and 13, 14 in the latitude dimension. And everything which is here is actually can be any Julia function that you want. Okay, so you even can put if this is time, you can even put, I want to have the first month, something like this. So it doesn't have to be a consecutive subset. Okay. what we also start to implement in common data model, because it's not really specific to NetCDF, but it's also available to NC datasets, is that you can group the data and reduce the data. So that's often called split, apply, combine, in the case of data frames. So you can split your data set using some criteria, or group your data set, and then reduce it. So one thing that's we often do, for example, is to compute the monthly mean, for example, of a satellite data cube. So where the data cube is longitude, latitude, and time, and assume that you have a daily time data set spanning over several years, and you want to compute the average of all January, February, and so on. So you would group the data set by months and then compute the mean. So that's also now implemented in common data model. So, and yeah, I'm trying to look first at the syntax, how it is done in X-array, because it's a quite popular package in the Python world. And something important to know that when you execute this command, it will be really fast because it doesn't do anything. So it is really just lazy. It doesn't actually compute the mean. It only computes the mean when you index this operation. Okay. So only if you have the SST mean, so this will be a three-dimensional array. If you just index it, then the computation will be done. Okay. And so we also overrode some broadcasting operation, so you can apply any function before the reduction. And another thing so once you have now your monthly mean, you sometimes want to compute the anomalies. So for every day in your satellite time series, you want to compute how is this different from the average January, average February conditions. And for this we overloaded the dot minus operator. So that's the climatological mean will then be automatically broadcasted to the full size to compute this difference. Okay. And what was also important to me is that these functions are extensible, so you can easily add your own grouping functions and your own reduction function if you want. So in X-array, you typically have to specify if the variable is called time, then you would use time.months, but this is encoded as a string. So if you don't want to use, so X-array is quite flexible, you have months, day of the year, and so on. But if you want to do something else, then it gets more complicated to add a new criteria to make your groups. But in this package here, you can actually use any Julia functions. Like if you want to define a season as the Atlantic hurricane season, you can do that. You could say, okay, that's between the 1st June and end of February, and you just define your function, is it within the Atlantic hurricane season, and then you group your data based on this. And then you can also reduce using other reduction function, like looking at the temperatures larger than 26 degrees, for example. And when I came here, my flight was delayed, so I worked a bit on this. So what I implemented is also the fact that you can now do a rolling window average. So like it's often called running average. Yeah. So the difference here that from a group by operation that the different groups actually do overlap. Yeah. So you have your data, and then you're sliding in a window. Say you want to make weekly average, you're sliding a window of 7 days over your whole data set. And that's also with a similar syntax than X-array. And in order to compute the variance, so variance and standard deviation, they're actually very different algorithm. So we had a look at, reviewed a bit the different ways to compute this and what are the typical precisions that you can expect. So the obvious way to compute the variance or standard deviation is to just first compute the mean and then subtract the mean of each value and then so you compute the anomalies and sum the anomalies squared. Okay. So but this direct way to do it means that either you need to load all the data in memory, yeah, and if you're using large netcdf files, that can be a problem, okay, or you have to pass twice over the data, once to compute the mean, and then a second time to compute the actual variance, okay, and that's not ideal. Yeah? So if you're working with large data sets, you definitely want to load all in memory, and loading them twice, that's slow as well. So,
Alexander?
Yes?
Can I ask a question?
Sure.
It was more to it was more to the rolling means and also to the group by and
for sure.
operations. Is it supported to do that over multiple netcdf files? Because I know, at least for me, it's quite common that I have a whole time series of different netcdf files in small slices.
Oh yeah, that's a really excellent question. So you can actually, when you open a netcdf file, so the constructor is called nc_dataset, yeah. But you can, instead of providing just a single file, you're providing a list of files. Then it will automatically concatenate all these netcdf files, and you can specify over which dimension you want to concatenate. So if the dimension is called time, so most often you split different netcdf files over time, then you specify that you aggregate all these files over time. And then you have a single dataset object which represents all your netcdf files.
Oh.
And then you can do everything what I explained here with a group by operation and subsetting and things like this.
And that also works when you have different groups in the netcdf file. That, let's say you have 3 different groups in the netcdf file that each have a time dimension, and you want to match on group and then on time.
So the files that you're concatenating have to be similar.
Okay.
So if they are too different, then you cannot really represent them as a single array anymore. So then I would have to look at actually what are your files. But for instance, the files do not have to have the same number of time instances, because they're just concatenated, but they do have to have the same spatial grid. Okay. So, but we can talk later on if you can give some examples. So, but typically they're expected to be similar.
Okay. Thank you.
But it's a very good question, because indeed most satellite data, it becomes unhandy to make a really huge file with all the time series. It's quite common to separate it in different files. Okay. So another approach to compute the variance, which is now a single pass algorithm, it's to compute the sum of each variable and the sum of each variable squared. Yeah? And then you have this property of the variance. That is just the difference between the average of the squared values and the squared values of the minus the squared values of the average. So this is a one-pass algorithm, but this is a really bad choice. So I'm just wondering if you see why is this a bad choice. So computing the standard deviation by averaging the squares minus the square of the average. Squaring? Squaring is it's just a multiplication. That's relatively fast, actually.
No, I mean that we have to. I think I passed it by that many years ago. There is another expression that you can call the standard deviation.
There's a better one. There's a better one. I will come to it. But actually, the main problem with this is that if the mean is not close to 0, you will end. Tell me.
It gets huge.
It gets huge. It gets really huge. Yeah, exactly. So you're subtracting 2 large quantities, and your value is a difference between 2 large quantities. So you use a lot of precision. So it can be really bad. So you're essentially halving the accuracy. So if you have typically 7 digits of accuracy, you will have just 3 digits of accuracy, something like this. So that's a big problem. So there are different ways to go around it. So essentially, you want to shift your data. You want to have a shift your data so that you are actually adding small numbers, not adding huge numbers together, accumulating huge numbers. So if you have a first estimate of the mean, it doesn't have to be perfect because the variance, if you shift the data by a constant factor, the variance remains the same. But the best algorithm I found so far is the well-forced online algorithm, which is really clever because it computes the mean so far and constantly reshifts the data. And the nice thing, this only goes once to the data and it preserves preserves essentially the accuracy. And so we did some benchmarks and comparison of our code, and we compared it to Xarray because it's really fairly well known in the Python community. So my test case here was just I have a two-dimensional array. Spatial dimension is just 360 by 180. So think of a 1 degree global data set, but you have 30 years of daily data. 30 years of daily data. So it's about 2 gigabytes, 3 gigabytes on this data. And it's just random data with a mean of 100 and a variance of 1. Okay? So if the mean would be actually 0, then I would not see any problem in precision because that would be the ideal case. But I decided to shift the mean and to put 100. And all the data is in single position and the computation is also in single position. So to see if there's a problem with precision to see it. And so we compute the mean and standard deviation. And in order to test the accuracy, we did the same thing for, we just took the data and compute mean and variance in double precision using directly statistics or for Xarray, the NumPy equivalent. And then we compute the RMS error scaled by the theoretical values. Okay. So in single precision, the smallest increment that you can typically represent is 10 to the minus 7. So you have 7 significant digits in a single precision. And so the test environment that I do, so it was very important to, when you read a data set from disk, what the operating system does is actually to keep it in cache. So if you're doing benchmarking, you will end up with speeds that are much faster than it actually will be, because when you're repeating the test, you're repeating the test like 30 times. The first time will be slow because it has to read the data, but then it will be in memory in the cache of the operating system. So it's you're no longer including the file access if you're not careful. So it's really important to drop the file cache before every computation in order to make it really realistic. If a user loads the data set and wants to compute the monthly mean, in this case, it's unlikely that it will be in cache either. Okay? And so we use just one, the default for Xarray, and for common data model, so we use just one CPU core. Okay, and we use the latest version of Xarray. And the code is also on GitHub. So if you want to test, if you want to look at the Python or Julia code, that's available there. And so Xarray it's a fairly mature package. So it has been developed for 10 years now, and it calls really specialized and well optimized code in C. Okay, so it is. So even though Xarray is a Python package, most of the computation are actually done in C. So I was not really sure if it will. So I was curious to see how it worked out. So typically, yeah. And when I run this on my workstation at the University of Liège, so the data is stored in the SSD, and I was actually quite surprised to see that the common data model mean and standard deviation is about. So if I get 10 seconds for Xarray, I get about 8 seconds, or so about 2 seconds faster for common data model. So that was quite encouraging. And the accuracy is what you would expect for single precision. So even though I use the way that I implemented the mean and standard deviation actually preserves the accuracy. And then I repeated the test on my laptop here, and this has a newer SSD. It has a NVMe SSD, and then you see that both X-array and common data model are much faster. Still, common data model is about 2 seconds faster than X-array, but now in relative terms it's even twice as fast, just because the I/O has become much faster. So for me, it's quite interesting to see that the storage becomes really fast, and it's no longer that accessing the disk is slow. So whatever you do later on, it doesn't really matter. So if you're waiting 10 seconds or a minute to load the data, if the computation later on just is 1 second or half a second, it really doesn't matter. But as the storage becomes much more quicker, much more faster, so I think it's increasingly important to think about that we implement efficient algorithm later on. And so I also had a look at really what X-array is doing using the nice debugger in Python. So you can run a code, interrupt it, and see what it's actually doing. And so the difference was that X-array is not loading the data sequentially. It's only, so it's loading all the data of January 1st and then computes the mean, then all of February and then computes the mean. So this is for this accessing the data randomly actually can result in some performance problems. While in common data model, for most of reduction operation like sum, mean, variance, standard deviation, minimum, and maximum, the data is loaded sequentially. So I load the data as they are stored on the disk. I look at the data, okay, you are January, you go to the mean to January, you are June, you're going to the mean of June, and so on. So you're loading the data sequentially, and that's much faster. But you cannot do this for every case. So for the median, for instance, I don't think that you can do the same approach. So there I only also use non-sequential access to the data, as it is in X-array. But I think that mean, variance, standard deviations are so common that it's quite worth to implement a quick optimized version for them. Okay, and all of this, or actually most of this, is available in the documentation as a tutorial for common data model. So if you want to have a look at this and reproduce some examples. Okay. So on Friday we will have a hackathon about a package which is called DivaND. So this allows you to make a interpolation of in situ observations, and this is actually one of the main reasons why we evolved in Julia, because this is the main toolbox that gives us most projects that we're working on. And so the idea is that when you have a cloud of observations, so it's discrete in situ observations, you want to produce an analyzed field from these discrete observations. And what you're doing, essentially, you want to produce a field which is as close as within the error bound of the observations, and also spatially smooth. Okay, you don't want to have any artifact, even if there's noise on the data. So this is formalized using a cost function. And in the workshop on Friday, actually, we are trying to do a little game. So I tell you, this is a true field. This is now ceaseless temperature, where with the only average mean removed. And then you get to decide where to put the observations in the ocean. Yeah. So you get to decide, you're a program manager of a funding grant, or you're a scientist. You get to decide where you should sample the ocean. And from this discrete location, you then computing the diva analysis, and then we are assessing how good this analysis is relative to the true field. So we'll never match the true field perfectly, because you cannot sample the ocean everywhere, but we can think about where are good locations to sample the ocean. Okay, so you can program also some strategies. So you can have a look at the field and say, okay, every time where I have a maximum or something, that's a maximum temperature, that's maybe a good location. Okay? So that will be on Friday. And now something very different is that I worked also on running Julia in the web browser. And this is possible thanks to WebAssembly, which is a binary code format. So the web browser cannot only execute JavaScript, but it can also execute WebAssembly. And so LLVM, the compiler on which Julia is based, can produce WebAssembly. So in theory, you can produce from Julia code, can go from Julia code to WebAssembly that can be run in the web browser. And so for this, I use the package which is called GPU compiler. So if you use CUDA or an AMD graphic cards, you're probably also using GPU compiler under the hood. So GPU compiler initially was developed to take Julia code and make it run on the GPU. But by now it's a fairly general package. It's not really specific to GPUs anymore. And you can declare another compiler type. There's some very interesting presentation made by somebody who managed to run Julia code on the Arduino, for instance. So these microcontrollers. And so this was one of my main motivation to try it, to test also to make it run on WebAssembly. There are some restrictions. So GPU compiler likes to have type-stable code, and it doesn't like to have allocation. Okay, and these are really, if you are implementing a model, if you're doing some number crunching in Julia, these are anyways things that you should do. So you should be careful that you have no type instability, and you have no allocation in hot loops, for instance. Okay. And by looking at how arrays are stored in memory in Julia, you can also you have to work around a bit how the things need to be laid out so that it can be found, so that it can be accessed on the JavaScript side and the Julia side. But this is a bit technical, so I'm not using the default array type. I'm using the malloc array type from static tools, because there's a very simple memory layout that I can then emulate in JavaScript. So here are some examples. The first example that I implement is the 2D Navier-Stokes equation, the 2D Charlotte equation, and the smooth particle hydrodynamics. All with a very similar approach. So if you are in front of your laptop, I invite you just to type this link here, tinyurl.com/JuliaWasm1, WASM in capital. And this is actually Julia code, which was compiled to WASM and then runs directly on the web, in your web browser. So this simulates the flow around a circular obstacle, and what you see in color is pressure, and you can also visualize its velocity. So red is high pressure, and blue is low pressure, and you can make it also interactively, so you can actually change the domain, and draw whatever you want, and then simulate the flow around it. So I guess most of you came by plane to Terceira Island. So if you draw here a section of a wing, and you can can convince yourself that the plane should actually fly, because you see that above the curved surface you have a lower pressure than below, and that creates the lift of the plane. And I found out that it's also useful distraction for kids. So so the kids played a lot with it, and to draw a lot of things in the domain. And yeah. Another thing I'm almost running out of time. So another thing that we did with students is to we asked them to build the drifter themselves, to build a device to measure ocean currents, which is a drifter which simply follows the ocean currents. And it was a quite fun project, and we used Julia as a data logger and to transmit the position. So for this, we use a Raspberry Pi and a special, not too expensive hardware to send positions via text message. So if one day you want to have your Julia code to send you a SMS that it's finished to do some computation, I have some code I can share it to you. Okay. So I think I will stop here, so that we still have time some questions. So I will not show really the last part, which is about denoising diffusion model, where we reconstruct missing data using a reverse diffusion process. I can give you more details about this if you are interested later on. So yeah. So in conclusion, so if we have changed NC dataset quite a bit. So a lot of things was factored out in another package called Common Data Model, which is not specific to NetCDF. I wanted this package to be called Abstract Datasets, but other people didn't like it, so I used it Common Data Model. And this package is used by grip datasets, which is made by Tristan, and you can use the same API to load grip data, and also for TIFF data and TIFF data sets. And so, yeah, and I think WebAssembly is a very cool technology in order to showcase some Julia code and to get people interested in what modeling activity are you doing. I think that's, there's a very low barrier entry to try something out. And there's also, I want to give a shout out to Tom Schultz's package, which is called WebAssembly Compiler, which helps you a lot. So I started to use my work before this existed, but I think when using this, a lot of restrictions can be circumvented. Okay, so thank you so much, and I'm happy to take any question. Yeah.
This TIFF dataset is already registered?
No, it's not registered. Good question. Yeah. If you want me to register it, I can register it. So if there is an interest, I can register it.
It's already using the common data model?
Yes.
It uses the native Julia TIFF package to read the TIFF file, or is it using GDO?
Yeah, exactly. Yeah, it's using GDA. Yeah. I've seen your suggestion. So I tried to use a native TIFF package, but it doesn't know the geo extension in TIFF. Mm-hmm. So it is, and GDAL does. So it's, I was not able to get projection information and things like this out of the TIFF package.
Got it. Thanks.
Yeah.
So the question, I'll repeat here for the online recording. So I was asking if the TIFF datasets package was already registered and if it's using the native Julia TIFF package to load, or is it using GDO?
Yeah,
so that's the question.
Anyway, the GTIFF package is maintained by the same guy that maintains GDAL, and the code is inside GDAL. So
I'm mentioning, so there's a Julia package called thief.jl or something like this, and it's the same guy that maintains.
No. The guy that maintains GDAL, he also maintains GeoTIFF-C, and is included in GDAL. So in fact, going from one way or the other should be the same.
Yeah, so I was mentioning, so there's a package in Julia for loading TIFF in native Julia. I was wondering if this package was used. There's nothing like a C library behind the scenes, just raw Julia loading TIFF. But there's no metadata, as Alex mentioned, like to load the geo TIFF part of the TIFF.
Yeah, that's another package. Julio was mentioned is this TIFF image. That's a native Julia package.
That's native Julia, yeah.
It does unfortunately not support the geo extension, so as far as I know, at least.
It's again to the TIFF data sets. I think I tried to use TIFF images, and it's also like support for like images that have complex values. Because I know at least for radar images, the TIFF format is sometimes used where the pixel values are complex, and that's I know ArchGDL supports that now. But so maybe TIFF datasets also does, but it's something that's. I mean, it's nice to consider for us radar people that actually the pixel values are also allowed to be complex.
Oh, that's interesting. I didn't know that GeoTIFFs allows this complex number. I didn't test it. I feel I should test it before I really say that it's supported. Okay. So, yeah. Okay.
Thank you once again, Alexander.
Thank you.